In this video, we're going to learn about optimization, and we're going to learn a few new vocabulary words in the process, like first-order condition and second-order condition. The optimization process is really just about finding the maximum and minimum values on a function. So, for example, if you have a graph that looks something like this parabola, and you're interested in finding this point, the place where the y value hits a maximum relative to the other y values around it, then that process is called optimization, finding the maxes and mins. And calculus has a really easy tool that we can use in order to find that point. And by that point, we really just mean the x-coordinate where it happens. And of course, you could also then plug that into the actual function to get the y-coordinate of it. But that's what we mean. We want to find that xy coordinate point where that function hits an extreme point. Because, in the real world, those are often useful applications. Like if this is your profits, this is showing how many units you need to sell in order to maximize your profits or something like that, among so many other things that you could want to maximize or minimize. So what is the first order condition mean? Well, before we talk about that, let's first just talk about how do you optimize a function. And the answer is really simple. You look for where the derivative, or the slope, is 0. Because here's the thing, looking at this parabola, if I were to look anywhere on this left half of it, the slope is a positive number. It's an upward sloping, equation, graph. And on the right half of it, it's a negative slope. The derivative is negative because it's sort of downward sloping if you look anywhere on there. And so here's the thing, ultimately, the only way a point can be a max or a min is if it's a flat slope over there, meaning it can't be a positive or a negative slope and still be a max or a min, because if you're a positive slope, then if you move a little bit to the right or a little bit to the left, it's going to basically not be as high as possible or as low as possible anymore. If I were to move a little bit to the right, something else is above, and so that means this point is not a maximum. And if I were to move a little bit to the left, then there's something lower, so it can't be a minimum. So really, that's why it's got to be flat as almost like a prerequisite, under normal conditions where you have a continuous function and you're looking at the entire domain, little things like that. So under normal circumstances, that's what we're looking for. We're looking for where's the derivative 0, because that's the only way you have a chance even of being an extreme point. So that's what we're looking for. And so how do we do that? How do we find where the first derivative is 0? Well, algebraically, you just find the equation of the first derivative and you set it equal to 0 and you solve for x. So this equation, the fact that the first derivative is 0, is called the first order condition. So again, the word first is because we're talking about the first derivative, or the slope, being equal to 0. So the condition, in order to be a max or a min, is one of the conditions, one of the two conditions, is that the first derivative equals 0. So this equation is the first order condition. So if a question says, on this function, find the FOC, that's what this stands for, first order condition. So find the FOC of this graph right here. So let's do it. So the FOC is really just saying, take the first derivative and set that equal to 0. So the first derivative here is going to be, let's see, f prime of x. The first derivative is, let's just go term by term. The derivative of negative x squared is negative 2x. The derivative of 12x is just 12, so plus 12. And the derivative of 8 is 0, because that's just a constant. So this is the first derivative, so the first order condition is just setting that equal to 0. So 0 equals negative 2x plus 12. So that's the first order condition. So now if the question then goes further and says, use this FOC, so this is again the FOC, use the FOC to find the x-coordinate point of the max or the min. Well, let's see. Let's just solve for it. We could just add 2x to both sides, and that would give us, starting this here, 2x equals 12, and then we divide both sides by 2 to get x equals 6. So here, that means that here, this coordinate point is x equals 6. And so that gives us the x-coordinate, and of course we could plug it back in here to help with the y-coordinate, right? So cool, simple enough. Take the derivative, set it to 0, and find the x-coordinate, and that's your first order condition. But here's the thing. The first order condition is not enough in order to know for sure that this is a maximum. Because here's the problem. If I were to give you a different graph that sort of just like looked like this, and all you did was, and this is just like a parabola that's opening upwards, and you took the first derivative, set it equal to 0, then basically you're going to get this point. But that's a minimum. That's not a maximum. So how do you know? How do you distinguish then, when your first derivative is set equal to 0, whether that point is a maximum or a minimum? Or heck, it could even be neither. Because what if your graph was like a cubic function that looks like this? Here, on this graph, it's flat over here when x is 0. So, for example, just y equals x cubed, the first order condition, we'll see the derivative is 3x squared, and so the first order condition is 0 equals that. And here x equals 0 meets that criteria. But where x equals 0, this function it's flat, but it's not a max nor, it's neither a max nor a min, right? So how can you then distinguish between, maxes, mins, or neithers once you know that the derivative is definitely 0 at that x coordinate point? And the answer is by using the second order condition. So the second order condition is giving us the conditions under which your sort of, this is what we call in math a critical point. So a critical point is just a point where the first order condition is met. So I'll just write that down here. Here x equals 6 would be considered a critical point. That's a critical point. So in order to then classify your critical point as a maximum, a minimum, or neither, you then look at the second order condition and you basically see at that x value, is your second derivative positive, negative, or 0? And here's why. Looking at this graph, if I were to ask you, at this maximum point, what's the first derivative? It's pretty clear it's 0 because it's flat. But if I were to ask you what's the second derivative, it should be obvious once you think about it that, oh, it's a negative second derivative because this function is concave down, or also called concave down, or that's also called concave, right? So there's convex and concave. And so in either case, if it's concave or down like this, then that means that the second derivative is negative. And if the second derivative is negative, and additionally it's a critical point, meaning the first derivative is 0, that then is sufficient for us to be able to claim that that point, at least locally, is a maximum, meaning locally compared to all the points around it, it's a maximum. So here's what the second order condition says, is that your second derivative, if your second derivative is negative for that critical point, then it's a maximum. Because if the second derivative is negative, as we saw in an earlier video, the second derivative is negative implies that the function is concave down. So here f would be concave down. And if the second derivative is positive, meaning it opens up like this, and additionally, and again, so notice if the second derivative is positive and it's concave up, that alone doesn't mean it's like a minimum point, because you could be over here or over here. Like, those aren't minimum points, even though the second derivative is positive. But if you're here, specifically where the first order condition is met, and on top of that, you know that the second order condition is met, those two combined tell you that that's a minimum, right? So you need both in order to establish that point of a max or a min. Cool. So here, this would imply that the function is concave up, or convex, if you're using that terminology. So essentially, if we have both met, then that's sufficient. So here, if we wanted to really show that this, where x is 6 on this graph, that this is, like, let's say we didn't know what the graph looked like. If you just started with this algebra, found the first order condition, and you wanted to then show that that's really a maximum, not a minimum, or let's say you don't even know if it's a max or mix, you want to find out, is this critical point a max or a min or neither, you then just take the derivative of the first derivative, right? You take the second derivative. So here, if I were to say what's is the second order condition met for this to be a maximum, well, let's see, let's find the f double prime. So the second derivative here, well, let's see, the second derivative of this is pretty easy, it's just negative 2, because the derivative of negative 2x is negative 2, and the derivative of 12 is 0, so it's negative 2. So normally what we do is, if your second derivative, has an x in it, you then plug in x equals 6, right? Whatever that critical point is that you're testing to see if it's a max or a min. So it's unlike the first order condition, there is no zero involved. When you take the second derivative, you do not set it equal to zero. You do not plug in zero for x. You plug in, you take the second derivative, you plug in the critical point, the x value, into there for x, and you see if that overall second derivative, the value, the numerical value, is positive, negative, or zero. If it's positive, then it's, again, concave up, and so it's a minimum. If it's negative, it's concave down. And if it's zero, then that's inconclusive. Usually that means that it might be neither, but there might be some further testing that you might have to do. But really, for the most part, for simple cases, it's like, all right, if it's neither of these two, then it's just neither. But in either case, so here, because this was negative, we didn't even need to plug in our x equals 6, because no matter what x you plug in, the second derivative is negative 2, which just means that this function is always concave down, which means that any critical points would necessarily be a maximum, right? Because the second derivative is always concave down no matter what x you plug in. So that's how we can establish that 6 comma whatever y value you get when you plug 6 into this equation over here, that point is a maximum, a local maximum. So that's the optimization process. Now let's try it with a different example. So here, let's say you have a graph, and it looks like this, and for now, let's not even assume where the maxes and mins are. This is, looking at this is some cubic function, right? It's a third degree polynomial, and so we know that it might look something like this n shape, but really, we don't know if it looks like this, or if it looks like, this, or what have you. We really don't know. So I just put that as like a, default image that comes to my mind when I think of a cubic function. But let's say we wanted to find the critical points on this and classify them as maxes or mins or neither, right? So here, how do we find those? Well, let's see. Let's just do the usual process. Take the derivative, set it to 0 for the first order condition. So the derivative here, g prime of t, let's see, the derivative here of 6t to the third power, the 2t to the third power, the 3 comes down, and you get 2 times 3 is 6, t squared, right? Because 3 minus 1. Minus, then the derivative of the second term, 21t squared. The 2 comes down, and you get 2 times 21, which is 42. So minus 42t to the first power, because that's the derivative of t squared, is t to the first power after we multiply by the 2. And then the derivative of 60t is just 60. And the derivative of the 100 is 0. So basically you have this guy. 6t squared minus 42t plus 60. So that's the derivative, so the first order condition is then setting that equal to 0. So 0 equals 6t squared minus 42t plus 60. So now here's where we gotta bust out our quadratics skills, because in order to find the first order condition, we need to solve for this quadratic equation. Now here you might notice that each of these three terms have a 6 in them, so you could factor out a 6, and you can just divide both sides by 6. If you divide both sides by 6, you get 0 equals t squared minus, 42 divided by 6 is 7, so 7t plus, and then 60 divided by 6 is 10, so you get this. And now here, if you factor, here I'm just going to erase this graph for now. So if you factor, you get, for this guy, 0 equals, and here you could factor this as, let's see, what two numbers multiply to give you 10, but add up to give you negative 7? Well, I guess 2 and 5, right? 2 times 5 is 10. But I guess if you use negative 2 and negative 5, they'll add up to be negative 7, but they'll still multiply to give you positive 10. So here I could factor that as t minus 2, t minus 5. And hey, when you solve for this, you get t equals 2 or t equals 5, right? If you set those equal to 0. So you get t equals 2 or t equals 5. So those are our two critical points. If we were graphing this, those are the two x values, 2 and 5, where the function is going to be flat, right? That's what this means. So notice, these aren't zeros. These aren't zeros. They would be zeros if this was the original function, but this was the derivative. So these are the two x values where the derivative is 0, meaning the function is flat. So it might look something like this, like flat here and flat here, or the other way around. It might look something like, like a minimum here and a maximum here, right? So we don't know which one of these is a mix, which one of these is a max, or or whatnot, but yeah, but those are the two critical points. So how can we then find out which of these is a max or a min? How do we classify these two critical points? And the answer is using the second order condition. So the second order condition, for that we find the second derivative. So the second derivative here, I'm just going to write this out over here. So g double prime of t, so just to copy the first derivative is, we got it all the way down to this guy, t squared, technically before we divided by the 6 we had this, but even after we factored out the 6 we had it down to t squared minus 7t plus 10. So t squared minus 7t plus 10. And like I said, technically the first derivative was that times 6. So then when we take the second derivative, meaning the derivative of that, the 6 can just sort of go along for the ride. It really doesn't matter here. But so the derivative then of this term is 2t minus 7, right? So 2t minus 7, and that 10 drops. And then, yeah, times 6. And so the times 6 won't make a difference because, again, if it's a constant, it just gets multiplied throughout for when you take the derivative, so you don't need to worry about it. But also, it's a positive number, and so it's not going to change the sign of the second derivative. So, yeah. So now, again, we don't set this equal to 0 or anything. We basically plug in this and see if it's positive or negative. So what is the second derivative's value when x is 2, or t is 2? Well, let's just plug it in. 2 times 2 minus 7. And so that's going to be 2 times 2 is 4. 4 minus 7 is a negative number. So here, g prime of 2 is some negative number. We don't even need to know what the exact number is. All that matters is that it's negative. Meaning, this over here is a maximum. So if graphing it, it sort of looks like this. It's going to be a maximum because it's a negative second derivative. And similarly at 5, when you plug in 5 for t, you get 2 times, so g of 5, g double prime of 5, is going to be 2t minus 7. So that's going to be positive. That's going to be 10 minus 7, which is 3 times 6. So again, a positive number. So g double prime of 5 is a positive number, meaning the function is concave up. And so when you look at it, again, this is like a concave up smiley face, right? Versus upside down smiley face for concave down. So this is a concave up function. It's concave up, but it's a critical point, meaning it's flat. And so that is what makes it a minimum. And that's what makes 2 a maximum, because it's concave down and it's flat. So now we've classified. So notice, without even knowing how to graph this, we were able to graph it very precisely. We know the overall shape, and we specifically know where the max and min is for this function. And if we were to plug it into the original, we could even get the y-coordinates of those 2 points. So that's first and second order conditions. Now, finally, let's end with just an application problem. So let's say you're given that your profit as a business as a function of your marketing expenditures M is given by this equation. And you want to find the marketing expenses. So overall, in this problem, I guess, the more you spend on marketing, the more your profits are, but at some point, it's probably going to go down if you spend a whole bunch on marketing. So we want to find how is profit maximized based on your marketing expenses M, and you know, how much, and again, a question can even go as far as to ask for the y-coordinate point there by saying, what's the highest profit level you can make? So, but in either case, let's just for now find the M value. What's the M that maximizes your profits? So what do? First order condition is that the derivative is 0. So let's find the first order condition. Let's take the derivative of this and set it equal to 0. So the derivative of this of ln of m squared, let's see, the derivative of a log function is just 1 over what's on the inside, 1 over m squared. And then chain rule times the derivative of the inside, which is 2m, so times 2m, minus the derivative of m over 200. Well, if you think about it, that's like literally 1 over 200 as a constant, so minus 1 over 200m. And again, this is no different in my mind than saying what's the derivative of 3x. It's just that constant 3. So similarly, the derivative of this constant times your variable m is just that constant. No quotient rule or anything needed here. That's only if you have a variable on the top and the bottom, right? So in either case, the derivative of this is just negative 1 over 200. That's the derivative of this term, and the derivative of this term we got here. Here the m's can cancel. So you have basically 2 over m. So this is really just p prime, which we're going to set, let's just set that equal to 0. So 0 equals, this simplifies to 2 over m, because the 2m over m squared. The m's cancel, so just 2 over m minus 1 over 200. So we could now add 1 over 200 to both sides. So if we do that, we get, I'll just write this here. So if we add 1 over 200 to both sides, we get 1 over 200 equals 2 over m. Cross multiply, and we get, let's see, when we cross multiply, we get m equals 400, right? Because m times 1 is m, and then 200 times 2 is 400, so you get m equals 400. So what this means is that if you spend 400 on marketing, then the derivative of profits is 0. But what we don't know is whether that's a maximum or minimum. I just drew this graph at random. I don't know what the graph of this guy looks like. It might look like this, and in that case, we've minimized our profits, right? So what we want to do is check our second order condition. So if the first derivative was this was our p prime, the simplest version of it. So the p double prime, let's just write this out here. So here your p double prime, second derivative, let's see. The derivative of 2 over m is, well, let's see, for that, because your variable's in the bottom, I would rewrite 2 over m as 2m. So I'm just going to rewrite my derivative here as 2m to the negative 1. That's 2m to the negative 1 because I'm on the bottom, minus 1 over 200. That won't matter because that's a constant. So when you take the derivative now, this drops because that's just a constant. And the derivative of 2m to the negative 1, let's see, the negative 1 comes down. So you get negative 2m to the negative 2, right? Because you subtract 1 from that exponent. And that m to the negative 2 is like an m squared in the denominator. So finally, this is negative 2 over m squared. And now, when we plug in m is 400, well, 400 squared, whatever it is, it's still a positive number. And negative 2 divided by that is still a negative number. So overall, we know that at our critical point, p double prime is negative. And so our second order condition is met for maximizing a function, right? So if your second derivative is negative at the critical point, then that means, in fact, you've maximized the function rather than minimized the function.